Today, announcement to you today is about the development of engine control logic. My name is PS Kim. I belong to Hyundai Motor Company. I would like to explain the background of the development of control logic in HMC. And next, our team is developing engine and transmission control logic. The structure of the ECU and TCU is described as below. It can be classified in 4 types. The first, application software, the basic software, CPU-dependent software, ECU hardware. Our software development process proceeds as follows. The first, application software is control logic related to engine and vehicle driving. The ASCII is used as a tool to develop application software. The application software .A12 and C code and header file are created as a result. Next, when the developer will proceed the modeling in the module based on the requirement of part or system. Usually, the function consists of the several modules. After the modeling in the modules is finished, the working is integrated in each function. And then, simulation will proceed to verify the function is working as planned. Once the developer has been validated this function, and next ask the integration officer to ask each function into the project. After that, and C code are generated and A12 is generated. Here is A12 is only about application software. This process is logic development process for application software using ASCII. ASCII SCM. ASCII SCM is used by developers to share their modules they are responsible for. SCM means source code management. To use the SCM, we must connect the server. You can enter the repository address and ID in SCM setting. You only need to do once at the beginning of the ASCII. And the modules, it is stored on the server in the form of the G file. This G file contains information such as the revision number and ID and date created. If you want to save the modules developed by others on your PC, you can get the checkout. But in this case, all the logic is made public. When accessing another company or another team, access is restricted by granting access to each folder. Maybe it's access denied, for example. ASCII project environment in project editor. Check the type and implementation variable used between the modules. That is, they check whether it is integer type or continuous type or signed unsigned type, a variable type. And next, assign the task to run the module. For example, each modules have the process. Maybe, for example, this module has two tasks of process. 1,000 run and post start. This process has two tasks. This is shown the project task. There's many kind of the task. If we run this module, this task assigning to project task. And then next, the formula setting. To change the hex value to the appropriate physical value and exploit edit. And the next is generate code and write A12. When application software related to A12 is created in ASCII, there are 3 types of A12 at this time. Application software, basic software, and diagnostic software. These 3 types of A12 are integrated into one. This is done using the tool called the IFG. IFG stands for Integration and Form B Generator. IFG has 3 characteristics. The first, server-based code integration management. That is, if you revision number of the application software or basic software, the BPM is inputted to here. The code information corresponding to this revision number are downloaded and build can be started. The diagnosis information is included to here, and the BPM means BPM stands for build process management, and which is responsible for post-processing after compiling and linking. When you know this revision number, we are building in an environment when the ROM was created at any time, and all the build process from the code generation to ROM creation are integrated in the IFG. The details are very complicated to set up, but once the setup is completed, it is very convenient. When the capable of the driving, capable of engine and driving is created in ASCII, the specification should be provided so that this logic can be operated. Compared to PDF, the e-handbook has some advantages. The first, model block in specification will be continuously blown inside and out. If you want to see the inside of this block, you just click to here, and as the inside of the block is expanded out to here, the details can be checked. And it is easy to grasp the structure of the control logic. You can easily see whether this variable it is used and how it is calculated here. And if you click the variable on the e-handbook, you can see the information of the variable. For example, about this variable for wiper, you can see the description and formula type and the data type, etc. And next, you can add this variable direct to add to Inca experiment. E-handbook specification creation process is very simple. It takes the necessary information from the ASCII workspace and convert it into the e-handbook container and link the necessary information and create the file with the EHB. To read the EHB, the e-handbook navigator will can be needed. We are if we distribute the test team, we will provide the first final A12 and Hexa and EHP specification and the e-handbook navigator. And how to create e-handbook specification is very simple. And this tool and click, and it does click and the generate a document and enter information and blah 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 and click here, and is generate an e-handbook specification. Okay, this is what I have prepared today.
Ich werde den ersten Teil.
I am going to cover the first part of this presentation. Thomas Bleile will then take over. We are going to present two new methods, two new tools for the development of complex systems. One is called SCODE, and the other one is called Congra. And I'm going to tell you the story behind these two tools, what we can do with them, and Thomas Bleile will then show you how this is used at DGS. This is the history behind it. 10 years ago, in research, we started to develop SCODE. Well, why did we do that? We looked at software. All the software was very complex, and it was getting more and more complex. And then we were asked to develop something to change this. And we said, okay, we have to get to the root of the problem and develop a completely new method. And this is how we came up with SCODE. Constraint graphs, that's Congra, that came 5 years later. That's when we said, okay, we've got SCODE and we reduced complexity, but now we want to do more in the field of control engineering. And this is how we came up with Congra. SCODE is about 10 years old, Congra is about 5 years old, and this is also the experience or the period in which we were able to gain experience. So SCODE and constraint graphs were covered in the last few years. Congra is a little bit younger, so we've worked so far much more with SCODE than with Congra. But this year we've been getting very active to really also take this out and bring this to the market. What do we address? Well, based on Bosch's history, we look at everything that is in the realm of system and control engineering, software developing, and the development of ECU code, because that's what the aim is. We want to have code for our ECUs. So that was important for our research. The final result has got to be the code for our ECUs. So from the requirements, from the idea of a system, of a function, up to the ECU code, this is the chain, the structure that we want to support. So here you can see the different fields that we've been working in. Most prominently, that was actually the first system that we covered, that was the air system, both the controllers and the plant model. But there were other areas that we worked on, for example, in the field of chassis control. We looked at brake systems, ABS and ESP, but also more novel systems that we supported with our method, with this new method. And you can also see that there are some more recent things, such as electrical engines, hybrid vehicles. Bosch, as you know, also produces refrigerators, so we also used it in that field. And we even worked with a motorcycle manufacturer, and it was about making sure that the ESP for the high-speed motorcycle was working properly. So it's not only the conventional powertrain, but we have new drive systems that we can support. And take a look at the statement below. because most of what we actually did there was already existent. Only very few systems are in fact new systems. You know, you don't develop a brake system from scratch, do you? So time, manpower, and money has already been invested, and then the functions were reviewed with this new method, SCODI and Congra. Well, why was that the case? And that was actually the question that was put to us. We have reached an extremely high level of complexity in our software. Why is this the case, and how can we get rid of this? So we looked at the air system of the diesel, for example, and we looked at the physics of it. And the complexity in physics is much less than what we found in the software. And when I talk about software, no matter whether I say C or ASCII or MATLAB or Simulink or what have you, what we found, the paradigm, was the same everywhere. And then, of course, there were some problems such as errors that were found too late as on the test bench or as late as in the field. And there's a second aspect here. We had very low reuse. So if we wanted new controllers, then these controllers were drafted again in Simulink, in ASCII. So everything was done all over again. And of course, this is prone to errors, and for the sheer complexity of it, and this is what we wanted to reduce. So we came up with SCODI, System CO Design, SCODI. So it is all about reducing complexity, and in abstract terms, you can see the main finding that leads to complexity. No matter whether it's C, ASCII, or Simulink, you always find that something is decided, a switch, then there is some computation, then there's a decision, more computation, decision. So whether these are switches or characteristic maps, a plus, a switch, or in C, if else, if else, if else. You know, that's what you find. And this is the reason why all our software is so complex. What does SCODI do now? Well, SCODI removes all the switches. It collects all the switches, and we drastically reduce them. So the pure share of control is then left, no decisions left anymore. So we can then look at the sheer maths of the whole logic. SCODI is a three-step approach. The first step is that we define a problem space. We say, well, our function, what kind of information does it need? What can happen in the environment so that our function needs to know? And what can our function do in response? For example, operate an actuator or send a signal or whatever. So we look at this in the full combinatorial, combinations. So we define a lot in maths. You say combinatorial explosion. That's what it's called in maths. And we actually confront this very actively. So we ended up saying complexity is our friend. Of course, nobody wants more complexity. You don't want to be confronted with complexity. But for us, it wasn't a problem because we had the maths to cope with it. And the power of the SCODI approach comes with our second step. What we do is we cluster all the combinations. We have to handle all these combinations, but we cluster them in modes so that we have two properties. The first property is everything we define is treated completely and fully. So we don't skip any combination. So no matter which factors combine in the environment, we always have a response. And that is something that wasn't the case in the past, because there were coincidences where the system didn't respond appropriately, the system crashed, or it didn't respond. And since we are now working with the pure maths of it, we can cover 100% of it. And then also modes free of overlaps. So if x larger than 3, if x larger than 5 from the colleague. So how you combine them, there's a dependency of which dominates what. And when you had a dynamic scheduler, and then during driving, the runtime era, then the system was switching in a completely different way. And we said we want a deterministic switching behavior. So we need overlap-free modes, disjunct modes. That's how you call it in maths. And we will also do this if you want to get from one mode to the other, mode transitions. And this gives us a number of benefits, and it's actually a side effect. We have 100% coverage of test cases. So we analyzed everything, and we came up with the perfect partitioning of the switching behavior of every system based on the logic in the system. Back then, I sat in the software development department, and the control engineers were across the hallway. So they came and said, you've got a perfect mathematical model. We want the same for control engineering as well. So we looked at block diagrams and wondered, what are the problems with block diagrams? Well, there are two problems. We cannot implement them locally. That's what you would want to do as a control engineer. And we have algebraic loops. That's a huge problem. Warning, algebraic loop, what can you do? What you usually do is you introduce a unit delay, and you do not really know what kind of dynamics you get from there. So we said, let's do the same as in Escodi. We don't start in a directional way, like in a block diagram, but let's start off without direction. So as a user, I say, this is my structure. You can see an equation and a graph. That's why we call it a constraint graph. And I say, I know these two, so I can compute a set. So all the computation is done with no fault, with no error. So that's a differential equation. This is how you describe your plant model or your controllers. And for each Scodi mode that you've derived, you say, okay, that's my input, this is my output, this is my input. I will compute the output based on the same structure. And the idea behind it is that the physics don't change. My basic equation doesn't change. I can apply it everywhere. Or another thing like sensitivity analysis, the question of, well, I have an output value, for example, some vibration. Which of these 50 parameters are the ones that I have to touch? Or which two inputs actually dominate the fact that this behavior is generated at the output? And on a conventional system, that's quite difficult. And here it is more or easier. And we can do other things of time discretization. So if you want to have a plant model or if you want to take it towards software, we always need to transition towards time discretization so that we can work along our time grid from differential equation to a difference equation. Block diagrams only allow for explicits if you don't change the direction, but block diagrams are directional. Explicit processes, however, have difficult stability constraints. A millisecond grid, and that's fine. So in this case, we can do discretization at any time. Without conditions, it is stable. So I can have it run on a slower grid, and the controller as such is stable. Of course, I have to look at the plant model still, but I have fewer problems. And this is what Thomas will comment on later on as to how we've done this at DGS. So what did we do with Scode? We filled the frame, and from one model, we said, okay, let's generate all the different possibilities. And another thing that we can do is we can generate code, we can have ESDL, M-files, Simulink blocks, everything can be generated from there. And what have we achieved? Well, that's what Thomas is going to show you based on the example of DGS.
Genau, das heißt, ich möchte Ihnen jetzt zeigen, wie diese...
Yes, I would like to show you the effect of these methods when they are applied, for example, to an air system of a diesel engine. So it's about filling the combustion chamber with the right amount of fuel and air, and we've got the throttle available for that and the intake valve. And we looked at the equations and how we can model this. And the function that was the result is on the right-hand side, is depicted on the right-hand side. What's of interest for us are only the parts that are encircled in red, because these are the switches. And if you take a look at the switches, you will come up with a number of 30. And that's surprising because we said, okay, we looked at a physical approach. Actually, we were expecting complicated equations and many, many equations, but why do we end up with 30 switches? If you do control engineering, you look at matrix inversion and what have you, very complex maths. But no switches. But if you open up our control ECU software, then you will find switches. And this is exactly what we address with Escode. We have lots of switches, and these switches are scattered. They're scattered everywhere because we will set switches only where we need them in a block diagram. They are local switches where I have to decide, do we go left-hand side or right-hand side? Min, max are switches. That's not continuous, it's a switch, especially when you go to the C code level. You will see that it is a switch. So 30 switches. So 20 to the power of 2 to the power of 30 possibilities, that's 1 billion possibilities. So what's your gut feeling? Say I have a hair system, I want to control 2 parameters. I have 1 billion possibilities to come from the input parameter to the output parameter without being a system expert. Do you think you can cope with that? No, it's much too much. You cannot cope with it at all. So which of these 1 billion possibilities do we need, after all? And this is exactly what Escode is about. Now, the question to the system expert is, well, why can't you do it without a switch? Kick out all the switches, you get your input parameters, you compute, and then you get the output parameter. It would be great to test, great to understand, do it like that. And then the function expert will say, well, stop it, you know. There are customers that want to control an EGR rate or air mass. Sometimes I've got to control both of that, or my DPF has got to be regenerated. And then this is the reason why they cannot always do the same. And this is exactly what we have in this wiki box. These are potential reasons for switches. And this can be covered by Escode. And then it's like you just sort it from A to B. This is the function that I want to be able to do, and the other one, I don't need that. So we need to be complete, and you need to be unambiguous. This is what we did in the air system, and we didn't come up with 1 billion possibilities, but with 10 possibilities. It's exactly 10 possibilities to get from the input to the output, and we can be sure that we've covered all of them. And that's decisive. I mean, if you had looked at all the 1 billion, or at the billion possibilities, maybe you would have been able to reduce this to 9 or to 10, but you would never have been sure whether you had covered everything. But we now can cover everything. We will be sure that we covered everything. Then you can visualize it with such a tree, but it's just a visualization. It's always based on the same basis. It's a common databases. It's crisp mathematically, unambiguous, and from there you can derive different interpretations or visualizations, such as a tree, like that. And if you now take a look and say, okay, I'm in mode 1, I want in normal operation, throttle valve is open, everything that describes the situation you're actually in, then you can address each and every switch. Do I know where it is? If you know, then you switch it there and then you throw it away. And if you do that, you will end up with this. This is active when you're in one mode, in mode 1. But finding this in this kind of complexity, you won't find it. And you can reduce complexity. The beauty of the function is now visible because on the left-hand side it was hidden. Now this is how we can manage the control flow. Now let's turn to the data flow. I know what I have to compute. Now I have to do the actual computing. So there is a second approach that was presented by Mr. Behle. These are our constraint graphs. Congra. So I said it's not directional. I don't say this is my input and that's where I want to go. I take my equation. There's no directionality in the equation. And whether I want to compute mass or pressure because I know the mass, or mass because I know the pressure, and this undirected or non-directional graph depends on the mode. Depending on the mode, I have a different parameter that I know and the other one that I want to compute. So had we started with the constraint graphs, we would have ended up with the SCODI. Historically, it was the other way around. We started off with SCODI and came up with the constraint graphs Congra. So depending on the mode, the graph has to be directed differently. But because all directed graphs are based on the same undirected graph, then it doesn't matter whether the solution comes from the right to the left or is computed from the left to the right or from the left to the from the right to the left or from the left to the right. They are consistent. So you also have algebraic loops here. These algebraic loops can be resolved directly in the tool. The algebraic loops are directional. There are modes where they emerge and other modes where they don't emerge, and you can do this in real time. We're not talking about simulation. This is real time. So let's bring all this together. On the left-hand side, we've got the physical system. We decide what we want to do. When do we need to switch? Which are the different requirements? That's SCODI. We describe the physics with equations, that's Congra. From both tools we generate code from SCODI, and then we can put that together and implement it in the control unit as code. And this is what we did. So we bring the two together, and the level of abstractions at which we model is one level higher. So whether you you generate MATLAB or ASCII code, that doesn't matter. You are kind of one level up, and that helps because abstraction reduces complexity. So I presented one function to you. You can say, well, of course, it's always nice to have one pilot that works. But we have now more than 300 functions that we implemented. Sorry, 200 are implemented, and the plan for next year is to get to more than 300. And from the 200 that we've implemented, we've measured before and after the size of the rectangular. Stands for lines of code, so number of C statements. And you can see how we were able to reduce that. And the color depicts complexity. That's the Bosch maintainability index, matrix complexity, and so on, just in order to have a kind of figure which gives you an indication of how complex it is. So red means more complex, yellow is less complex, and green is least complex. And this is where we started off. These are the 200 functions, and this is the result. You can see the trend is clear, is towards green, and the rectangular itself is smaller. So I'd like to thank you for your attention, and I'm available for your questions.
Mich würde interessieren, ob Sie eine
I'd be interested whether you've considered ECU resources before and after, or S-code compared to what a human person has optimized for runtime and memory. Well, you can see that the code was reduced, that was improved. In terms of runtime, we are neutral or even a little better. You saw the overview. If you know in which mode you are, then there are many things that you don't even have to compute anymore. And this is how you get to either neutral or even better. I wouldn't use SCODI with the aim of reducing runtime. No, it's about reducing the complexity of functions. That's, that's the actual motivation behind it.
Good afternoon, everybody. First of all, I'd like to say thanks for coming to this session. I know some interesting competition in the main hall, so it's good to see everybody here. I'd like to talk about speeding up development with internal bypass solutions. So I'd like to start by examining why there's a need to speed up software development, and then go on to explain how bypass solutions can help with that. And in particular, why internal bypass is a really good solution for speeding up software development in today's market. So obviously we'd like to increase the efficiency all the way across that V-cycle, but for the purposes of this talk, I want to focus on this bit. So more efficient function development and prototyping. So here the OEM wants to develop their own distinctive control functionality. So they start by using Simulink or maybe ASCET from ETAS to develop their new function. And then they want to do some early validation of that prototype in a realistic setting, in a realistic environment. And they do function prototyping to do that. So how can bypass help with this? So the bypass concept then starts with the function developer having their new Simulink or ASCET model. And they want to do this realistic validation. So bypass is a good way to do this. We assume with bypass experiments that there is an existing ECU software and hardware. And normally the experiment will be done on some kind of development ECU with existing software and an appropriate ECU interface to allow data exchange to and from the ECU. And then the new control function is connected in to the existing software and effectively bypasses the functions that they are ultimately designed to replace. So one important aspect of bypass is that is the workflow between the OEM and the Tier 1. The OEM will develop their new software function, and they need to do the bypass experiment. But to do that, they'll need a special version of the software that has some software hooks placed in there to allow them to connect their new function to the existing ECU software. So that's a main prerequisite of doing bypass, and it assumes that there's effective cooperation between the Tier 1 and the OEM. So there are two basic configurations, external and internal bypass. External bypass, the new function runs on some dedicated external prototyping hardware, and the inputs and outputs to the ECU are provided by some fast ECU connection normally. The advantages of this setup are that you can run the prototype on target close external prototyping hardware, which will have a real-time operating system, similar or probably maybe even identical to the real ECU. And it's got high computational power and large amounts of memory, which means you can incorporate large complex prototypes. And the time in performance is pretty good also. It can go down to cycle times of about 200 microseconds, which is good for most applications, at least in the powertrain business. The alternative is internal bypass, where the new functions actually run directly on the ECU. And obviously to do this requires free ECU memory. So sometimes the size of the new function is limited by the ECU resources. But if you can work with that constraint, then the benefits are that it's a simple setup because you don't need any additional hardware and software. And that also makes it a relatively low-cost solution. And it's realistic because the prototype runs directly on the ECU. It's triggered by the ECU's operating system. And there's no added round-trip time, so there's no added time latency. So the timing behavior is always correct. And that makes it a really good application for these new functions with the fastest cycle times we're starting to see in today's market. So why internal bypass? If we take a closer look at the internal bypass use case then, looking at the ETAS example, so the function developer will have his new ASCET or Simulink model, and he will use eHooks to integrate that model directly into the ECU software. Once that's flashed down to the ECU, they can then do their bypass experiment using the Inca experiment environment connected to the ECU with some appropriate interface module. For high performance applications, they can use an ETK-based connection to the ECU for high bandwidth and low latency, or for less demanding applications, you can also use a CAN-based connection. With the Inca, it's also possible to run internal bypass experiments on more than one ECU simultaneously, so that makes this a good solution for distributed functions that run on multiple ECUs at the same time. So really the main benefit here is it is a simple solution, relatively low cost, but I think the big advantage is that the new function runs in the realistic environment, and the timing behavior will always be correct because it's triggered by the ECU's operating system and there's no added time latency. So when you combine this, let's say, intrinsic benefit of internal bypass with the use of an FETK connection to the ECU, for example, you can it allows data acquisition from functions running with cycle times down to about 10 microseconds. So 10 microseconds, it's very fast. So this makes this the perfect solution for validation of functions running even in the fastest cycle times we're seeing in today's market. So one of the problems that can occur with bypass experiments, as I mentioned before, is this the workflow between the OEM and the Tier 1. So the OEM develops their new function and they want to do a bypass experiment. But to do that, they need a special version of the software with some hooks placed in it. And so they have to make that request, and that has to be planned and implemented by the software development team at the ECU supplier, and that takes time. But when it arrives, the OEM can start to do their bypass experiment, and typically that takes a few iterations as they learn how to optimize the new functions, and that can also require more than one software delivery. So they have to go back and request another delivery. That needs to be planned and implemented, and that takes some time as well. But eventually it arrives. But there's a problem here with the whole turnaround time between the OEM and the Tier 1. And that can lead to delays of, typically it can be several weeks. In the worst cases, it can be several months. So for the OEM, under those circumstances, rapid prototyping doesn't look that rapid anymore. So there is a solution. The solution is for the ECU supplier to do a one-time preparation of their ECU software so that it can be used with eHooks. And then that's sent to the OEM customer. And then they can use eHooks themselves to insert the hooks in the software, start the bypass experiments, and when they need to do second and third iterations, they don't need to go back to the Tier 1 this time. They can just run eHooks again and change the hook configuration and change the function that's integrated into the software. So it's almost immediate modification when they have eHooks. And this alone can save OEMs weeks or months of development time off their project timescales. So what eHooks does then is allow the OEM user to place these hooks directly in the ECU software without any Tier 1 involvement, without any access to the source code or the software build environment. And of course that provides great flexibility to quickly customize bypass experiments. And it allows them to take more control over the prototyping process, and that can directly help them to develop this distinctiveness that they're aiming for in less time and at lower cost. So if you take a little bit of a closer look at what eHooks actually does then, it inserts hook functions into the ECU software to bypass individual variables. And each hook function looks like this. It's basically a software switch, and the switch is turned on and off with a hook enabler, which is just a characteristic that's created by eHooks, and that can be controlled at runtime using Inca to turn the switch on or off. So when the hook's on, some bypass variable is written to the ECU measurement, and when the hook's off, the original ECU calculation is written. So eHooks can insert several different types of hook into the software, ranging from very simple hooks which replace the value with a characteristic or a constant value. That's useful for simple calibration or software testing use cases. But what we're really interested in for function development is eHooks can insert this thing called an on-target bypass hook, which takes the value directly from the new Simulink or ASCET function that's running in the ECU software. And because it's a variable hook, it allows the function developer to bypass the whole of an ECU function or just part of it, depending on what the use case is. So it gives them a high degree of control over how they actually do the bypass experiment. So in addition to placing hooks into the software, eHooks can also be used to actually integrate the new function into the ECU software. So for Simulink users, it provides an eHooks block set, and the Simulink user can work as normal from within Simulink to develop their model. And then they can add eHooks blocks, so they can add an eHooks read block to read ECU measurements into their model, and they can add eHooks write blocks to write back the results of the model calculation into the ECU software. And this is actually the block that creates the on-target bypass hooks that I talked about in the last slide. Not shown on here. There's also a trigger block which allows the user to configure how the model is executed in the ECU. So once all the configuration's done, the user can build the software as normal from Simulink. Simulink will generate the model code, and eHooks takes over, generates the hook code, compiles all the new code, and then merges it with the existing ECU and hex file to produce this new modified hex and A2L file, which now contains the Simulink model. And when that's flashed down to the ECU, of course, you're good to go with your bypass experiment. So that's Simulink. eHooks also provides a similar integration with ASCET. So for function developers who use ASCET, they can use eHooks to configure the reads and writes into their model and configure how the model's triggered. And again, simply build from ASCET to produce this new ECU software with the model included. Okay, so now I'd like to move on and just look at some of the benefits of internal bypass in the context of electric-powered vehicle development. So one of the challenges here, as I mentioned it briefly before, is we're seeing the emergence of much more complex systems. Obviously in the midterm with hybrid electric vehicles, the systems are much more complex in the past. And I think here that internal bypass offers a good solution because it's intrinsically a simple system. It doesn't require any additional hardware or software to run the prototype. And so this intrinsic simplicity can help to control and mitigate the overall development complexity for function development teams. Another challenge here is the emergence of faster functions to control electric-powered vehicles. So we're starting to see functions that run with cycle times down to about 100 microseconds in electric motor controllers, compared with about 1 microsecond for conventional internal combustion engines. So that's about 10 times faster than the fastest ECU functions we're used to seeing. So here again, I think internal bypass is a really good solution because, as I've said, it runs on the ECU. The new function runs on the ECU. It can be triggered in the fastest ECU rasters. And there's no added latency. There's no round trip times to worry about. So the timing behavior is always correct. So we're also seeing the emergence of these more distributed functions. For example, energy management system in electric-powered vehicles is distributed throughout multiple ECUs. And again, I think here internal bypass offers a really nice solution because, as we've seen, Incra allows you to conduct the experiment on multiple ECUs at the same time. You don't need additional hardware and software on each ECU to do this experiment. And the timing behavior is always correct, so it's a good solution here as well. And finally, I think this is maybe the last one, more of an opportunity than a challenge, but in these type of vehicles, we're seeing bigger ECUs with more computational power and more memory. And actually, that's an opportunity for internal bypass because it gives us the potential to integrate bigger, more complex functions than has been possible in the past. So I think this is an opportunity, and in combination with all the benefits of internal bypass, I think we're likely to see it used more and more as a validation technique in the future, especially in the powertrain market. So this is my last slide, almost finished. Just to summarize, really, we've seen internal bypass offers multiple benefits, and I think those benefits are becoming more relevant to these new technologies we're seeing, particularly in powertrain with electric-powered vehicles, but maybe also outside of powertrain because there's new opportunities to use this in chassis systems. Maybe it's relevant to ADAS. So it might, I think, spread outside of the powertrain domain to be used in chassis systems in future. And when it's used, we've seen that it can actually result in new control functions being brought to market faster through speeding up the software development process. It can help improve the quality through earlier validation in this realistic environment, and it can help to control costs through being an intrinsically simple setup and also helping to reduce the number of software deliveries that take place between the OEM and the Tier 1.
How can or could eHooks be used not only to kind of a rapid prototyping thing where somebody wants to change, an OEM wants to change the behavior of a function, but to use it as a kind of an infrastructure to develop test cases? For example, you can simulate a broken sensor. Just so how far do customers go? So you could even implement a microservices architecture because you could just, if you design your software to be eHooks centric, you could actually replace any function with any other function. So do customers do that?
Yeah, no, it's a great question, Arndt, actually, because I've just really concentrated on one use case here because I only had 20 minutes. But I alluded to the fact that eHooks is used by calibration teams. It's also used in some cases by software testing teams because actually it's a perfect technology for injecting test data right into the heart of the software. And it simplifies the software testing use case quite significantly because you don't need to connect, external signals from on hardware pins. So it's not I would say function development is still the majority use case, followed probably by calibration teams. But I think there's real potential for using eHooks more in the future for software testing. And you're right, you could incorporate a new function onto the ECU software that basically just generates test data and feed that into other parts of the software. So at the moment, it's kind of at the early stages, I would say, but there's definitely more potential to use eHooks in that domain, yeah.